we can get started. Yeah. So today we're extremely pleased to have Abhay Pasupathy to talk about the paired density wave. Recently, paired density wave have been extremely popular. There are many Nature papers, talk about paired density wave, and Abhay has discovered something that's sort of unique in iron-based superconductor on this particular material. Basically, is actually induced by sort of a magnetism, not from iron itself, but from the rare earth. If I'm quoting him or not quoting him, if I'm thinking this correctly. Yeah, so I heard his talk briefly in Japan. I really really enjoyed the talk. So I'm hoping he can present this to a much broader audience. Abhay is very well known in the community, for doing his STM work for many years, and he's a well-known figure. And now actually he has an interesting appointment, not only at Columbia but also at Brookhaven. So he has two bosses, one for Columbia, one for DOE. Yeah, Abhay, it's all yours.
Okay, thank you very much, Peng. Let me first correct you and say that I did nothing here. So I should give the credit to the persons who actually did the work. So He Zhao, who is a postdoc in our group at Brookhaven. So this work is mostly done at Brookhaven, actually. Is the person who actually did the work. Can you hear me? Peng, can you hear me?
Yes.
Okay. Okay.
Yeah, loud and clear. I muted myself to get a better recording. Yeah.
Okay.
Yeah, keep going.
Yeah. So her and is one of the primary movers of this work, and Raymond is another postdoc also in our group, and our group, scan probe microscopy group at Brookhaven, along with me, the other co-PI is Kazuo Fujita, who is also a longtime STM expert. So this particular project, I'm going to talk about an interesting material and our STM measurements on this material. As Peng already said, it's iron pnictide, so it has iron arsenic. That's the basic superconducting unit, but it also has a magnetic element in it, europium. And I'm going to essentially tell you a story of how this magnetism and superconductivity interact with each other. And these samples come from the group of Hiroshi Esaki, in Japan, beautiful samples with which now we're doing other measurements as well. And we also did some Raman spectroscopy measurements, which my student Morgan, together with my colleague Xiaoyang Zhu at Columbia, we did these measurements. So the work that I'll talk about here, for the most part, is published in this recent paper, but I'll also show you a little bit of unpublished work. And as Peng said, that there's a bunch of papers on similar topics of this paired density wave, and I'll point you towards work on uranium ditelluride by Vidya Madhavan's group, and also Seamus Davis's group, and also Jian Wang's group on grain boundaries in iron selenide, which have also seen somewhat similar phenomena. So Peng told me that there's a lot of students here, at least when Tomo has done this, there's been students. And so I thought I would try to give a little bit of perspective, perhaps from somewhat far away for a student. And I thought I'd give you a somewhat my own perspective on why this topic is interesting to me. And I'd like to start by sort of reminding all of us, when we do quantum mechanics, how we are taught to think about a quantum mechanical system. One of the most basic things that all of us learn about in our quantum mechanics class is this concept of the two-level system. And so we think of a system where there's two quantum levels, and there is some object that inhabits these two quantum levels. Let's say it's an electron, and this electron can make transitions from one of these quantum levels to the other quantum level with a photon. So if it absorbs some light, then it can go from the ground state to the excited state, or it can decay from the excited state and go back to the ground state and give out some light, for example. And we're all taught that an atom, a real single atom, is sort of a good manifestation of something like this, right? It's kind of like this ideal two-level system. Now, if you ask yourself, what does a real atom look like, and to what extent does it look like this idealization? The answer is that, well, it's not exactly the same thing. if I take a real atom has many electrons in it, might be tens of electrons. It also has a nucleus. The nucleus has many nucleons, also tens of nucleons. And a real atom does not exist in some mythical space. It exists in real space. And the way it's kept in real space is by using some laser field, for example, to trap it in some potential like this. And so this atom can actually move as a whole in this potential way. And so the atom actually doesn't have just this ideal two-level structure. It has many degrees of freedom, some tens of different degrees of freedom for each of these electrons and nucleons. Plus, it can also vibrate in this trap. But if you are a good experimentalist and you choose a good atom, then what you can do is you can basically approximate this system by this very simple two-level system by just cooling things down to low temperature, making sure that it's not knocking into other atoms, and choosing the right kind of transition. And then to a large extent, you can approximate this more complicated beast, this atom, by this simple two-level system. And as you know, this two-level system is really at the heart of many of the things we think about when we think about modern quantum information, for example. So quantum computing and all these sorts of things are based on this idealization, this ideal two-level system. And so atoms are sort of one way of reaching this thing. And let me contrast this with how we think about a superconductor, and in particular, the sort of uniform superconductor that we learn about when we learn BCS theory. So what we're taught in the textbook is that if you're at high temperature, when the material is not a superconductor, it's just a simple metal, then this metal consists of, in a solid, consists of a macroscopic number of electrons, 10 to the 23 electrons. And each of these electrons has some description, so you can describe it either as a position of the electron or the momentum of the electron. And the electron also has some spin, which can be in some direction. And so if I think about what the wave function that describes this solid at room temperature is, it's just a terrible, terrible mess. I have to consider all the possible states of all these possible electrons and the spins and so on. Now, when we cool this material down and we make this into a superconductor, then once again, if you go and read your BCS theory textbook, we are taught that the reason that this material becomes a superconductor is because the electrons pair up. So now there is some effective attractive interaction between pairs of electrons, and pairs of electrons then condense into some superconducting state. And in the traditional superconductor, this is formed from a spin singlet state. So now the spin degree of freedom is quenched if they all form singlets. But even in the superconducting state, there are still many, many, many degrees of freedom that are possible. So these electrons are still moving around like crazy in a metal. And so if I was to write down a real wave function of all of these things, it still might be just terribly, terribly complicated. Now, the magic of the superconductor is that we know that even though the superconductor has all of these degrees of freedom, many of the experimental properties of the superconductor we can understand without really getting into the details of all of these individual degrees of freedom. But we can understand these experimental properties by simply considering the superconductor to be one complex number. And this we call the order parameter of the superconductor. So we can think of the superconductor as described by a complex number. This complex number has an amplitude. The amplitude is roughly the strength of the superconductor, or proportional to the superconducting transition temperature. And there's also a phase in this complex number. And in the situation where this superconductor is in a vacuum, not connected to anything, then this phase of the superconductor is just chosen arbitrarily, some number between 0 and 2 pi. And if I have this very, very simple picture of what a superconductor is, it's a complex number. And if I have some expression for how the energy of the superconductor depends on this number, which I'm not going to write down here, but there's some expression for it, using that very simple picture, we can explain many different physical phenomena. For example, I can explain to you why there should be a Meissner effect, why superconductors should be repelled by a magnetic field. I can explain to you how MRI magnets work, what a persistent current is. I can even explain for you what a Josephson junction is. A Josephson junction is two pieces of superconductor that are touching each other very weakly. I can explain to you how current flows in a Josephson junction, for example. And if you have two of these Josephson junctions, you form a squid, which is how you can detect a magnetic field, for example. I can explain to you how this squid magnetometer works. And going further, I can even take a modern superconducting qubit, so-called transmon qubit, and I can explain the properties of this object, all using this very simple conceptual understanding of a superconductor. That is, a superconductor is a complex number. Okay? And so this is sort of one of the real beauties of nature, is that this very complicated system is described by this very simple complex number. And we can ask ourselves the question, are all superconductors like this? Are all superconductors, can I just describe them with one complex number and then life is done? And the answer is that, at least theoretically, it has been postulated that there are many different types of superconducting orders. And the one that we see most commonly in nature is just that. It's the one that we see most commonly in nature, but by no means is it the only one that's possible. So just to give you one very reasonably recent example of something that's different from this simple uniform superconductor, this is a set of beautiful experiments done a few years ago in Maryland, studying this interesting material, uranium ditelluride. And if you look at the properties of this material, uranium ditelluride, what I show here is the specific heat capacity of uranium ditelluride. And I hope all of you see that there's sort of two bumps in the specific heat capacity. And the interpretation of this data are that in this material, there's actually two separate superconducting order parameters. So two separate superconductors living inside one material. And so if I have such a material where there's two separate superconducting order parameters, I need at least two complex numbers, psi1 and psi2, to describe its physical properties. And since a superconductor involves charged particles, anytime I have two orders, each of which involve charged particles, there will always be interactions between this. And so these two superconducting orders necessarily have to have some sort of interaction with each other. And one might ask, if one has such a material which is described not by one complex number, but is described by two complex numbers, then what kinds of properties would it have? Can we manipulate some of these properties and use them in new kinds of quantum devices, for example, and so on and so forth. Right? And so therefore, to sort of get my view of why this topic is very interesting in general, is to ask what kinds of superconductors might exist beyond the simple single complex number superconductor that we learn about in our basic BCS theory. So with that said, now let me kind of get a little bit into the specifics of the material that we are going to study. And I'm going to try to introduce this with a closely related effect that's seen in other superconductors, which I'll take you through in a few minutes. So let's now come back to the basic superconductor, basic BCS superconductor, and our textbook understanding of what this object is. So the way we understand a superconductor is you take a metal. A metal is described by a band structure, and here I'm drawing this band structure right here. And if this is a simple metal with no spin orbit coupling, then for every spin up electron with a certain momentum, I have a spin down electron also with the same momentum, and I also have spin down electrons with opposite momenta. And in the simplest basic superconductor, we take an electron with a momentum k and another electron with momentum minus k, and the two of them get together and form a spin singlet state, and they form, they're attracted effectively and form a pair. Right? And this we call the Cooper pair. Now you can ask yourselves, how can we start messing with this basic picture? And one of the ways we can mess with this picture is to introduce spin-orbit coupling into the system. So if you have spin-orbit coupling into the system, so just to say that, sorry, before I go there, this basic picture that is drawn here for a single band continues to be true even if the material is a real material that's much more complicated, like aluminum. If I take aluminum, it has many bands. That's the Fermi surface of aluminum. Even though it's much more complicated than that simple one-dimensional picture that I drew, this basic phenomenon that you can form these kinds of spin singlet Cooper pairs still continues to remain true. Okay, so the first way we can mess with the basic superconductor is to introduce spin-orbit coupling. And there's different types of spin-orbit coupling. But basically what spin-orbit coupling will do is, if I pick a particular point in momentum, if I pick a particular k, then the energy of the upspin and the energy of the downspin are no longer the same at that particular value of momentum. And that's because of the famous spin-orbit coupling, where there's a coupling between the orbital motion of the electron and the electron spin. However, if I just have spin-orbit coupling and nothing more complicated than that, it is still true that if I look at a particular point in momentum and I consider the opposite momentum minus k, it's still possible to find for every state ek up, you'll find a state E minus K down, as long as time reversal symmetry is preserved. And so in such a situation, even though I have spin-orbit coupling present, I can still have majority spin singlet pairing, like I was telling you about before, and life goes on more or less the same. To look more carefully, the details are slightly involved, and there's a beautiful work on it from Gorkov and Rashba, which you can go back and read about this. Okay, now how about applying a magnetic field to a superconductor? So let's imagine first that a material is not a superconductor, it's just a normal metal, and it has a band structure given by this white line here. And I go ahead and I apply a magnetic field to it. Remember, the material is not a superconductor. So when I do this, then immediately there's a Zeeman effect. And so the spin up and the spin down no longer have the same energy, and they're separated by the Zeeman energy. And so this picture here is supposed to illustrate that. So you have the white line for one spin orientation and the green line for the opposite spin orientation. And now if I look at this band structure, if I take a particular k with spin up and I go to minus k, I have the same spin projection. I don't have the opposite spin projection at that particular minus k. And so what this says is that a magnetic field with the Zeeman effect is not good for the kind of superconductivity that I described to you earlier. And so in real life, if I take a real superconductor and I apply a small magnetic field to it, then what the superconductor prefers to do is it prefers to give up the Zeeman energy. So it prefers not to do this. And instead, it stays as a regular superconductor and has spin singlet Cooper pairing. Of course, this can only work up to a maximum magnetic field. If I make the magnetic field so large that the energy gain that it gets from the Zeeman effect is much larger than the energy gain that it gets from being a superconductor, then the superconductor is going to say, forget about this. I don't want to be a superconductor anymore. I would rather just be a normal metal and take advantage of the Zeeman effect. And this happens roughly when the magnitude of the Zeeman effect, which is G times mu B times B, is of the order of the superconducting energy scale. And this is a so-called Pauli limit of a superconductor. Now, many years ago, so this goes back to work in the early 60s, two groups of people, Fulde and Ferrell, and Larkin and Ovchinnikov, wrote two separate papers where they said that in the presence of a large magnetic field, it's still possible for a superconductor to be a superconductor, but at the same time also take some advantage of the Zeeman effect. And so here, let me take you through their proposal. So what they said is basically take the normal state of the superconductor and include the Zeeman effect, so now spin up and spin down are no longer degenerate with each other, one should be able to form a Cooper pair not with momentum k and minus k, but between momentum k, which is this guy, and momentum minus k plus q. Right? And so that then forms a Cooper pair like this. And one can ask ourselves, what's bad about forming this kind of Cooper pair? And the answer is, if I form this kind of Cooper pair, if I consider the total momentum of this pair, which is k minus k plus q, the total momentum of this pair is q. And that means that every pair of electrons here has a non-zero center of mass momentum, which means that viscous kinetic energy,
Pete is coming. I didn't ask yet, but I will walk down the hall.
I think I have a little bit of interference. Let me see if, okay, fine. Yeah, so pairs like this have a non-zero center of mass momentum. And if they have a non-zero center of mass momentum, this means this thing costs energy. And so the only reason that this superconductor would want to form is because it makes use of the Zeeman energy. It lowers its energy by making use of the Zeeman energy. And it takes a little bit of gain by forming the superconducting state with this non-zero center of mass momentum, right? And this particular state is called the FF state. And at the same time, Larkin and Ovchinnikov proposed a very closely related but slightly different state, which is called the LO state. And in the LO state, what they proposed is that you have pairs of electrons between k and minus k plus q, so that has net center of mass momentum q, and you also have pairs with minus k and k minus q, so the net center of mass momentum is minus q. So this is basically pairing between this point, and also this point and this point at the same time. And as you can see, these are very closely related states. Now you can ask yourself, in such a superconductor, what does the gap, what does the superconducting order parameter look like? And the answer is that in this particular case, the superconducting order parameter psi is, once again, it's a complex number. It's a complex number with an amplitude, where the amplitude is delta. But now the phase is no longer a constant in space, but the phase is winding in space. So psi looks like delta e to the IQR. And in the other case, the LO case, this looks like a combination of delta e to the IQR that comes from this guy, and delta e to the minus IQR that comes from this guy. And so you put both together, you have e to the plus IQR and e to the minus IQR, and that is a cosine of QR. So in the LO state, if I look at the superconducting order parameter, the superconducting order parameter in this case looks like a real number, but the magnitude of that superconducting order parameter is changing in space. It's moving sinusoidally or cosinusoidally. Whereas in the other state, this FF state, the amplitude of the superconducting order parameter is a constant in space, but the phase of the superconductor is winding in space in equilibrium. So I don't have to apply a voltage to the superconductor to make this happen. It's just in equilibrium, this would happen. And collectively, these two states, people call them the FFLO state. And there has been, a lot of beautiful work done to try to look for evidence of this FFLO state in a number of different materials at high magnetic field. And so generically, if you ask yourself, where would this FFLO state show up in a measurement, you want to be at low temperature, but at high magnetic field. And just before the material turns into the normal state, one might expect a little bit of this FFLO state to appear. And so a number of different experiments have been performed to look for this. I think there's some evidence of this in a number of different materials. I put down some of these here. Basically, the experiments either look like thermodynamic measurements, where you look at heat capacity, looking for multiple transitions, Or there are measurements like, for example, NMR, where the idea is that if I have a non-constant gap in space, then the different regions would give me different signals in NMR. And so I would see, for example, two lines in two peaks in NMR that is indicative of this kind of modulated superconductor in real space. Okay, so this is all, the theory for this was in the 60s. Experiments, I would say, are still ongoing. And there is a closely related set of experiments which was done about 20 years ago, which is the following. In this idea for the FFLO state, all of this physics came from the fact that you applied a magnetic field to a superconductor. And so people asked, well, why do you really need to apply a magnetic field to a superconductor? Why not take a superconductor and just place it on top of a ferromagnet? And the exchange coupling between the ferromagnet and the superconductor will serve the same purpose of the magnetic field. And so if you look near the edge of the superconductor as you go into the ferromagnet, one might expect the same sort of FFLO order to, I'm sorry, my computer is just running around. One might expect the order parameter to show similar sinusoidal variations. And there have even been some interesting device proposals, so-called pi junctions and so on, that have been proposed using this concept. And there's a nice review article here from 2005 if you're interested in learning more about this. I would say that this kind of research always ran into a little bit of problem because the way you made these kinds of samples was you evaporated a ferromagnet and then you perhaps oxidize the interface and then put in a superconductor. And when you grow materials like this by thin film growth, it's always very difficult to get a beautiful interface. Not to say it's impossible, there's lots of beautiful work done along this direction, but it's just a difficult thing to do. And so in our work, in what I'm going to tell you about, I'm going to tell you about a natural material which achieves this kind of structure, which has a superconductor and a ferromagnet just naturally present within one single crystal. But a couple of final slides of introduction before I get to the data on our particular material. All of the stuff that I talked about earlier is in the context of applying a magnetic field to a superconductor. More recently, about maybe 20 years ago, there was a proposal that it could be possible for a superconductor to have this kind of modulated superconductivity, to have order parameter that's modulated in space, even without any external magnetic field present. Right? So just by itself, the superconducting order parameter has these kinds of modulations in it. And one might ask, well, why would a superconductor ever want to do that? And let me give you at least one hypothetical example where this might appear. Imagine I have a material where, for whatever reason, the electrons segregate themselves in space and form stripes like this. So electrons are present only in this blue region here and this blue region here, and then there'll be another blue region here. If this is the case, then the interaction between these stripes naturally has a wavelength, and that wavelength is associated with the distance between these stripes. And so the interaction naturally has some cosine of QR built into it. And then the superconductivity might also have the same cosine of QR built into it. And so this is just a hand-waving picture for why such a state might occur. But generically, such a state is called a pair density wave. It's a state where, without the presence of any external magnetic field, one has a superconducting order parameter that's modulated in space. And I should say that as of now, I don't think there's any good evidence in any material for the presence of such an order. I should not say there's not good evidence. There's evidence for some of these things in some materials, but nothing that's conclusive just yet, in my opinion. And this is true even in our material that I'm going to talk about. There's magnetism that's present that plays an important role, unlike this situation where there's no magnetism present. Okay, I should also say one final thing. This is for the experts of the aficionados in the audience. There are many materials which have density wave orders like charge density waves or spin density waves, and also superconductivity at the same time. For example, niobium diselenite is a famous example which has both a charge order as well as superconductivity that's present at the same time. Whenever I have these two orders both present at the same time, it is inevitable that the superconducting order is also going to become modulated in space. And this by itself should be no surprise, because charge order, again, has charge, and superconductivity is also a charged order. And so anytime you have both of these present, there's going to be some interaction between the two order parameters. And so the superconductivity is going to be modulated. And this by itself, while it's an interesting topic to ask how the superconductivity is modulated by the presence of the charge order, is fundamentally something that we expect. And if you want to read a little bit more about numbers and so on, there's a recent work on the archive on this. Okay, so this is all sort of a large introduction to the material of interest. And so now let me get to our material and what we've been studying over the past 2 years on this material. The material, as I said to you, is a magnetic iron pnictide. So it has layers of iron and arsenic. These are the superconducting layers. And it also has, it also has layers of europium, and the europium is a magnet. And if you ask what the magnetism of the europium looks like, then each layer of europium has a magnetic moment which is in plane. It's a ferromagnet in plane, 2 equals 0. But if I look out of plane, then every layer of europium rotates its magnetization by 90 degrees with respect to the previous layer that's below it. And so as I go up, it forms this kind of helical or spiral structure as I go along the c-axis. Now, as I should say that this helical or spiral order is quite weak. And so if I apply a small magnetic field as small as half a Tesla in pretty much any direction, then I can get all of the moments to line up in whichever direction I want. So at roughly half a Tesla, the material is basically a ferromagnet. It points in whatever direction that you want it to. Now, what's beautiful about this material, and there's a number of such materials, is that this material is also a superconductor at the same time as it is a magnet. And if you look at the heat capacity of this material, it shows a very clear superconducting transition temperature. This is quite high in temperature. This is around 36 Kelvin here. And as you cool down, interestingly, the magnetism sets in at a lower temperature. Magnetism in this compound sets in around 15 Kelvin. And you can again see the magnetic transition in the heat capacity very, very well. I should also say for the pnictide experts in the audience, the electronic structure of this material, while it is complicated, looks somewhat like most of the other pnictides that we know. They have hole pockets near the center of the Brillouin zone and electron pockets near the corners of the Brillouin zone, much like many of the other pnictide compounds that we know. Okay, so what do we do in our experiment? We're doing scanning tunneling microscopy. So what we do is we take a single crystal of this material and we cleave it in vacuum. So we just break the surface. And when you do that with 90% of the time, the place where the material breaks is on this rubidium layer. That just is the most natural place for it to cleave. And so what is exposed is the rubidium layer, and below the rubidium layer is the iron arsenic layer, which is a superconducting layer. And below that iron arsenic layer is the magnetic layer. And so the magnetic layer in these measurements is actually hidden to us. It's kind of 2 levels below where we scan. And all the implications about magnetism, we don't directly measure magnetism in our experiments. We just measure the local density of states with STM measurements. And so when you cleave this material, it cleaves quite nicely. It gives you flat surfaces. And between these flat surfaces, you can see unit cell steps. So 1.33 nanometers is the unit cell height of this material. And if you zoom in, you can see atoms of the material and so on. one of the things I want to impress on you, because I'm going to show you some data later about the superconductivity. If I just look at the structure of the material, so if I just go with my STM and I probe around on the surface and I ask what the structure of this material is, you will see many defects, and that's because any material in the world has defects in it. But these defects are not ordered, so they have no structure in them. If I take the Fourier transform of this real space image, in reciprocal space, you'll see noise, and this noise is just because of the Fourier transform of these random pixels. But there's no surface reconstruction or other sort of orders in these materials, and no detectable long-range modulations in the surface topography of this material. Now, what we can do with the STM is we can measure the local density of states. So this is STM spectroscopy. So we measure the differential conductance as a function of bias that we apply between the tip and the sample. And we can see very clearly as we go below the superconducting transition temperature, this is 35 Kelvin, you start to see a little gap appear in the spectrum. That's a signature of superconductivity. And as you go down to low temperature, this is 8 Kelvin, you can see this gap develop into a nice superconducting gap, as many superconductors have. Now, these measurements that I'm showing you right here are taken at one particular point on the sample. So I just park my tip over one particular atom and I take these measurements, and this is what one might get. And the interesting thing that we want to ask in this material is what happens as I take my STM tip and I go from point to point and I measure how this gap changes from point to point. And so what I show you here is a surface topograph. And if I go along this white line and I measure the superconducting gap at every point in space, then what you can see, and let me zoom into the edge of this superconducting gap, is you can see that this gap modulates in a nice fashion, somewhat sinusoidally, as you go across in space. And so this was really the interesting finding that found when he first stuck in this sample, is that the gap is not constant in space, but instead it shows a sinusoidal modulation as you walk across the sample. And the period of this modulation is about 8 lattice constants along one of the principal axes of the crystal. Now, you can visualize this much better by doing the following. You pick a particular energy. So we pick this particular energy, which is the energy of the coherence peak. And I plot the density of states at this particular energy everywhere in space. We call that a conductance map. And if you do that, you can see, I hope all of you can now see very clearly, you see these unidirectional lines that run in this conductance map, which is basically visualizing the same thing. It is telling you that this superconducting gap is modulating in a sinusoidal fashion as I go across this in this particular direction. Now, I should say right here is that this does not fit the formula cosine of QR. If it fit cosine of QR, the gap should go to 0 somewhere. And clearly the gap does not go to 0 anywhere in space. There's always a gap. Instead, the formula that would accurately describe this is something like a constant delta 0 plus delta 1 times cosine of QR. That would be a formula that fits this. And something that you notice that we noticed that was very interesting is that these stripes are unidirectional. This material as a whole has 4-fold rotational symmetry, but these stripes that we observe breaks that 4-fold rotational symmetry, and therefore we call this a smectic after the liquid crystal language. So it's something that breaks the intrinsic rotational symmetry of the crystal. Okay, so this was our first observation that the superconducting gap displays these modulations. And we wanted to make sure, A, that this thing has something to do with the magnetism in the material, and B, that it has something to do with the superconducting order in this material. And so in order to see that it really has something to do with magnetism and with superconductivity, we did a few experiments that I'm now going to describe to you. So first, just to say, we can actually plot out what the superconducting gap looks like in real space, and you can see the same modulation in the superconducting gap that you saw on the last slide. And if you take a Fourier transform of this, you can see very clear spots, which tells you the wavelength of these stripes. And the wavelength of these stripes is, as I said, is approximately 8 lattice constants. And it's a beautiful long-range order. So we've seen many dozens of periods of these that have coherent modulation. So it looks like cosine of QR without phase slips. Yeah, so this is a line cut of this Fourier transform. You can see this peak, which is basically single pixel sharp, telling you that it's a nice, well-defined wavelength in the system. Okay, so now the first thing that I want to try to convince you is that this phenomenon that we're seeing is not a charge density wave. So a charge density wave is also something where the electrons break the translational symmetry of the crystal. But a charge density wave affects electrons at all energies. And this is because when you have a charge density wave, the atoms physically move. And when the atoms physically move, they're going to give you a new periodicity, and electrons at all energy scales are going to respond to this phenomenon. On the other hand, in our measurements, we see these modulations only at the superconducting energy scale, only at the energy scale delta naught. And even if you go to twice the superconducting gap magnitude, which is 12 millivolts in this case, which is also fairly low energy, these features all disappear. So it's not a charge density wave from STM measurements. We can look carefully at the energy dependence of the Fourier transform and also confirm this. We also did some other measurements. So these are Raman spectroscopy measurements. So typically when you have charge density waves or other types of density waves, then you see evidence for this in how the phonon modes of the crystal change as a function of temperature. And from this material, we can see that the phonon modes are basically unaffected by the presence of magnetism. And so we believe that there's really no charge density wave or spin density wave order that onsets at this temperature. Okay, so now we want to ask, how does this unidirectional stripe order change as I go through the magnetic transition temperature? And so in order to do this, we pick a region of the sample. We start at low temperature where we see these stripe modulations, and we raise the temperature and we look at this phenomenon. And as we do that, so this is 10 Kelvin, 15, which is just close to the magnetic transition temperature, and 18, which is just above the magnetic transition temperature. And I hope all of you see that when we go across the magnetic transition temperature, this phenomenon is gone. So this phenomenon really depends on the presence of the magnetism of the europium in order to exist. And if you look at the intensity of how these features die away as a function of temperature, this is similar to how magnetism itself in the material dies away as a function of temperature. So this is how the magnetism disappears from neutron diffraction. There's some similarity between how the magnetism disappears in intensity and our features disappear in STM. Now, the other thing that we'd like to really show is that this phenomenon is related to superconductivity. And in order to do this, what we do is we apply a magnetic field. And a magnetic field creates superconducting vortices. And here we apply a magnetic field of 9 Tesla. And when we apply this 9 Tesla magnetic field, you can see all the superconducting vortices in the sample very, very nicely. And inside a superconducting vortex, the superconducting order parameter is suppressed for the uniform superconductor. And so we can ask ourselves, does this phenomenon, these stripes that we see, does it persist inside the vortex and outside the vortex? Outside the vortex, even by eye, I hope all of you can see that these stripes still survive. So you can see these stripes beautifully running outside the vortex. Inside the vortex, looks like there's nothing. We can confirm this with a Fourier analysis. So what we do is we make a little mask that goes into the vortices. We just keep those regions of the sample and cut out everything else. And if we take a Fourier transform of just these regions of the sample, our modulated superconducting behavior is gone on the inside in the vortices. And just to be sure that this is not an artifact of our masking procedure, we can just shift the mask from this blue region down, we can just shift the same mask down, take the Fourier transform of these regions, and then you see this feature reappear at that wave vector. And so the point, I could have just made this point just by asking you to look at this image. The point that I want to make is that these modulations are gone inside the vortex. And so they're intimately related to the presence of the uniform superconductor. And therefore, the important point that I want to make is that this modulated superconductivity really requires both superconductivity and magnetism in order to exist. So it's some property that's an interaction between superconductivity and magnetism. Okay, so now let me just see how I'm doing in time. I'm at 45 minutes. So
yeah, you still have 10 minutes. Yeah.
Okay, so I will take
the
remaining time just to talk about some unpublished work that we're just preparing now for publication. And this is related to what the excitation spectrum of a superconductor is. And if you go back to the textbook and ask yourself, how do I calculate the excitations of the spectrum? Then here's how you do it. So imagine I have a normal metal. So this is a normal metal. And this yellow line is the chemical potential. And if I take a cut along this yellow line, and let's say this is in 2 dimensions, and I ask myself what the Fermi surface of the normal metal looks like, then the Fermi surface just looks like a circle for this particular band structure. When this material becomes a superconductor, then the prescription you have is the following. You take this white line, which is the normal state band structure, and you invert it. So you make it electron hole symmetric. That's this red dashed line. And you superpose these two on top of each other. That will give you a red Fermi surface and a white Fermi surface, both superposed on top of each other. And wherever these two intersect, a gap opens up. That gap is a superconducting gap. And so when I do this, I end up with a gap at the Fermi level. And if I go far away from the Fermi level, if I go up to here, I will have quasiparticle excitations of the superconductor. So that's our prescription for how to consider the excitation spectrum of a superconductor in this so-called semiconductor model. Is you construct the electron hole symmetric band structure, and wherever they intersect each other, you open up gaps. We can try to do the same thing for the FFLO state. So here is the FFLO state, or where, remember, there's a Zeeman effect. So there's a spin up and there's a spin down Fermi surface. That's the green one and the white one. And if I want to ask what the excitation spectrum of this particular superconductor is, now remember that the pairs are not formed between K and minus K. The pairs are formed between K and minus K plus Q. So I have to construct the particle hole symmetric band structure, and I have to shift them by this momentum Q, which is where the pairing happens. And so here there will be a gap that opens up, and here there will be a gap that opens up. But in general, there will be regions of the Fermi surface. So I'm showing this here at the Fermi surface. This part of the Fermi surface will indeed be gapped, and this part of the Fermi surface will be indeed gapped. But there are parts of the Fermi surface here. You see this part of the Fermi surface, or this part of the Fermi surface, where there will be no gap in this semiconductor model. And so this is sort of one of the predictions of these types of superconductors, these spare density wave superconductors or FFLO superconductors, is that generically at the Fermi level, the superconducting gap will not be on the entire Fermi surface. It could be, depending on the strength of the superconductor. But generically, there will be regions of the Fermi surface where there's quasiparticles even at the Fermi level. And this is something quite unique. Our regular superconductor has no quasiparticle excitations at the Fermi level. You have to go to an energy delta above the Fermi level in order to see these excitations. And recently, there have been sort of a bunch of beautiful works done on exploring these kinds of quasi-particle excitations. I give you just one of these papers. There's several of these papers. This is in a case where there's also spin-orbit coupling. So spin-orbit coupling plus a Zeeman field, if I have superconductivity, it can give you all these kinds of interesting Fermi surfaces at the Fermi surface excitations. And generically, people these days call this a Bogoliubov Fermi surface because it has both electron-like and hole-like Fermi surfaces present. Okay, so how do we see such Fermi surfaces in STM? And I'm going to give you a 1-minute tutorial to the students on how we see this. And this is using interference in an STM. So in an STM instrument, you can basically do 2 types of measurements, which are basically the same measurement, but it's looking at the data in different ways. One type of measurement, which is the type of measurement I've been showing you so far, is doing spectroscopy at a fixed position. So in this measurement, you sit at a particular point in space, and you apply a voltage between the tip and sample and measure the current. And then you measure a spectrum. This is the conductance of the junction as a function of voltage. And you would see, for example, the superconducting gap if this is a high TC superconductor. The other kind of measurement is we can pick a particular voltage difference or a particular energy of the tunneling quasiparticle, and we can measure at that particular energy, we can measure what the density of states looks like in space. And this is a very simple material, copper 111. If you look at copper 111 and you measure the density of states at some particular energy, you'll see this is a step edge in copper 111, but you'll see these beautiful wave-like fringes near the edges of the step. And this is nothing but interference. So how does this interference work? If I have a step edge in copper and I have an electron with momentum k at a given energy E, it bounces off the step. And if it bounces elastically, it goes back with momentum minus k at the same energy. And this incoming and outgoing wave are going to interfere with each other generically. And that's the momentum transfer in this is kf minus ki, which is twice k in this particular case. And so what this means is I'll see an interference pattern near the edge of the step. And the wavelength of this interference pattern, lambda, is proportional to 1 over this delta k. So by measuring the wavelength of these interference patterns, I can tell what the momentum of the electron was at that particular energy. Now, this is a special case of a step edge. In the more general case where I have different types of defects possible, then I will have all kinds of interesting scattering patterns. But the way we think about these scattering patterns is to say, if I have a particular Fermi surface, in this case, if I have a circular Fermi surface, I can ask myself, what are all the possible scatterings that are possible? And in this particular case, I can have a scattering from here to here, or here to here, or here, and so on. And if I consider the locus of all these possible scattering vectors for this particular simple Fermi surface, which is a circle, the locus of all possible scattering vectors is also a circle, but with a wave vector that is twice the original wave vector of the Fermi surface. And the reason for this is simple. The maximum possible scattering wave vector is from one end of the Fermi surface to the other. That's the backscattering wave vector. And so generically, we measure patterns like this by looking at the Fourier transform of STM data. And the presence of these interference patterns in real space tells us about what the reciprocal space band structure of the material was. Okay, so now what we want to do is we want to do this same measurement, but we want to do this at the Fermi level in our superconductor that has a pair density wave. And if you do that, so here, this is a real space interference pattern. I hope all of you can see that there's very clear patterns that are present in real space in this material. And again, this is at the Fermi level, where a simple superconductor will not have any excitations present. If I take a Fourier transform of this, you can once again see very, very clear spots present. And what this says is that a very simple message that since there are patterns, since there are interference patterns, well-defined scattering vectors, this means that there are quasiparticle excitations in this material at the Fermi level. Now, one thing we can do is we can take this data, this kind of data of the scattering pattern, and we can try to guess what is the Fermi surface that gives rise to such a scattering pattern. And if you play this game, you'll realize, if you think about it a little while, that the Fermi surface that gives rise to the scattering pattern that we see in the experiment looks like this. And this data are consistent with a partially gapped Fermi surface from the innermost hole pocket of this particular material, for those of you who are interested in that. Now, we can go above the magnetic transition, where, remember, I told you all of these phenomena go away. And indeed, if I go above the magnetic transition and I repeat the same measurement, all of these quasiparticles at low energy disappear in our interference patterns. And this is also consistent with our idea that the magnetism is really responsible for driving this unique superconducting order. And finally, let me just finish by saying we can look at the energy dependence of these patterns. So we can go to higher energies above the Fermi level. And as we go to higher energies above the Fermi level, we can see all of the quasiparticle excitations appear at higher energies. So here, for example, is at 5 millivolts above the Fermi level, you can see a full circle appear, and that's the full Fermi surface, where now there's quasiparticle excitations all across the Fermi surface. And using data like this, we can actually reconstruct what the superconducting gap function looks like in reciprocal space. And what we see is that indeed there are regions of reciprocal space where there's gapless regions of this Fermi surface, verifying that this indeed is this kind of Bogoliubov Fermi surface that was predicted from theory. So I think with this, let me stop, and let me just say that there's many other experiments that we're in the process of pursuing. This is an interesting material, an interesting class of materials, and there are many other measurements that we would like to perform, some of which are going on along with colleagues. And just to end and say, give you some perhaps interest in the future, in this particular material, nature gave for us a magnet and a superconductor, which are just one layer separated from each other. But these days, using all the magic of 2D materials, we can actually engineer such materials. So we can take one layer of a 2D magnet, and I can put it on one layer of a 2D superconductor. And so hopefully in the future, we can not only just realize such materials just by nature giving us such a material, but we can actually engineer such states and maybe even tune them in the future using electric and magnetic fields. So with that, thank you for taking the time.
Yeah, but very interesting talk. Yeah, Abhay, yeah. So let me sort of ask the first question. So I guess, I mean, for your magnetic order, modulation that you see, it has a particular direction. But the argument you have for the sort of a Zeeman effect, I would expect it to be, totally, sort of directional independent, right? Why does the modulation occur in a particular direction, of the domain that you're looking at?
Yes, so this is a good question. So to be honest, we don't know what sets the direction. So for example, you're right that when we apply an out-of-plane magnetic field, the moments of all the spins are pointing also out of plane.
Right.
And but the modulation that we still see is in plane, right? And
yeah.
So what sets that it should be this direction and not the orthogonal direction, we don't really know.
Do you see domains? I mean, with a large enough sample, you should see domains, right? That
yeah. So I think He has tried to see domains. What he has been able to see is if you sit in one region of the sample and you go sort of far away and go to another region of the sample, this stripe direction does rotate. But unfortunately, he's never been able to, STM sort of has a limited range, and he's never been able to actually see the interface between two of these. Probably the domains are just too large for us to sort of by luck hit on one of the domain boundaries.
Okay.
Yeah,
I see. Yeah, thank you.
It could also be that there's a small amount of strain in the sample. So anything like strain would pick one direction and make it inequivalent to another direction.
Okay, Alexei, yeah.
Do you hear me?
Yeah, sure.
The fact that there is no bulk observation of bulk pay density wave, does it suggest that the order you observe is actually surface order, not bulk?
Yeah, so this, it's certainly a possibility that this is only something that lives on the surface and does not live in the bulk, right? That would also be interesting. So
sure.
Some of the things that we're doing, so I think we're trying to see whether there's any evidence in X-ray measurements. So far, there's no evidence of this that we've seen. Tomo has done some USR. I need to talk to Tomo more. I believe, again, the data needs some interpretation. Something that we've seen in very recently in some electronic Raman measurements is something that's consistent with our story for there being very low energy quasiparticles. I think if you wait for another 6 months or so, we'll have a little more data to talk about that. But you're absolutely right. One would like to see if this phenomenon is there in the bulk of the sample. That would make it more fun for other measurements to also measure.
And I have another small question. So you observe only one gap. I think this material that have 3 whole bands and 3 gaps, 2, 5, and 8 millielectron volt. And you seem to observe only gap 5 millielectron volt, which suggests middle whole band. But on the last part of the talk, you say that your probe innermost whole band, which has gap 8 millielectron volt. Can you comment on that?
No, so I believe the innermost hole pocket has the smallest gap, and that's the one that we seem to see as mostly the modulated one.
No, I don't think so. In RPS shows that outmost gap has smallest gap of 2 millielectron, and this is also the least anisotropic gap.
Okay, let's discuss that perhaps offline.
Yeah. Okay.
We do see multiple gaps. So the largest gap, which is 8 millivolts, we do see that gap as well, and we see features on the inside of that gap. So of course we cannot momentum resolve the same way that RPS does, but in the shape of the spectrum, we do see the multiple gaps.
Ilya.
Yes, thank you very much, Abhay. Very nice talk. I have actually 2 questions. So the one is more or less a confusion, because when you were showing the data, you could clearly see that there is a very large uniform component of the gap.
Yeah.
It basically would mean that the analogy that you have shown to the FFLO state is not exactly correct. So there should be still complete gapping of the Fermi surface. So therefore, can you please clarify, you were discussing this residual volume of quasiparticles, but it cannot be then at 0 energy. So that's probably at the scale of the delta. That was a bit confusing. That's the first question.
Yeah, so the analogy with FFLO is precisely that. It's only an analogy with the FFLO. As I said, and you're absolutely right, that there's no place where the gap actually goes to 0, right? So in this case, it's a more complicated system. And as you know, there's sort of multiple pockets, right? And the question is, do all of the pockets have modulated superconductivity, or do only some of the pockets have modulated superconductivity? From our QPI data, we can explain most of the data by considering one of the whole pockets alone, based upon the Q that's measured from RPS and its modulations, right? But of course, there's always scattering. And so all the pockets have to have some effect of this in some way. The details of that and sort of a theory for that, I don't have. Yeah.
Okay, thank you very much. And the second short question in the same direction that Pinchenko has asked. When you were showing these nice Smectic directions, that was, however, taken at one particular bias, right, around the coherence peak. So I was wondering what will happen if you slightly go away, or if you go to the negative, for example, bias at the coherence peak, whether in that case orientation of the Smectic will change. So that's...
Yeah, so the orientation does not change. Let me see if I can pull up the slide to show you the energy dependence. I went through that a little bit quickly. Okay, so I'm not going to put it in wait, let me put it in full screen. So this is energy along the y-axis, and this is wave vector. So this is a cut through that direction of the modulation, and you see it really, the intensity of this feature only around the coherence peak energy. So this is 7 millivolts or something like that. But as you go to much higher energies, this is all just noise, and here there's nothing on the other side. So it's really around the superconducting energy scale that we see this feature. Okay. Does that make sense?
Thank you.
Yeah, Junhao. Yeah.
So are they very, very interesting results? So do you see a temperature dependence of the modulation wave vector Q? I mean, supposedly the Q is set by the exchange and then it should goes down as you getting close to the magnetic transition temperature.
Yeah, very good. So far we've looked for that, and we have no evidence so far for the change of Q. So you're absolutely right. If it's just an exchange splitting between the europium and the iron arsenide, then the magnitude of that exchange splitting might depend on the magnetization, which goes down as a function of temperature. Now, what does happen in our data, you can see as you go to 10 Kelvin, and then you go to 15, which is where really the intensity starts to die out. We start to lose intensity in our feature also. And so far, we have not really seen any evidence that this Q is changing. And this would be something that's against this sort of mean field, exchange field idea.
Yeah, okay, that's very good. Chetan?
Yeah, so I was wondering, you call it a Smectic, and there is a directionality in the Q, but somehow the QPI spectrum seems to have a fourfold symmetry. So I'm wondering how you reconcile the two.
Yeah, actually, it does not have a fourfold symmetry. So if you look at it carefully, so if you look at this carefully, you'll see that this spot is much more intense than this spot.
Yes.
And the angles, this angle is also not exactly 45 degrees with respect to this angle. So it actually breaks the fourfold rotational symmetry.
Okay, thank you.
Randy? Randy?
Yeah, hi, very nice talk.
Thank you.
We're involved in this area from a different perspective, from that of cold atoms. And our results have shown that in 3D and others in 2D, we couldn't find any evidence for FFLO. But in 1D or quasi 1D, near a 1D, 3D crossover, there was really very sensitive measurements of phase boundaries. I was wondering if you could comment on phase boundaries as a way of trying to characterize the FFLO phase, and also the role of dimensionality.
Yeah, so first is I'm aware of some of your seminal work, and I should have put some of those references in there. And so, you know, I think you're absolutely right that the original theory is like a one-dimensional theory, right? And as soon as you have more complicated Fermi surfaces, it's not clear that this phase will survive. And so, again, I think that's the reason why the phenomenon we see, while it might have something similar to the FFLO physics, I don't think it's a FFLO state, if that makes any sense. And now you asked about phase boundaries. Could you clarify what you mean by studying phase?
Yes, so in our work, we can, because we have an inhomogeneous density, we can see transitions to spatially resolved transitions from FFLO state to a ferromagnetic state, or FFLO to a BCS-like uniformly paired state.
Yeah, I see.
So I was wondering if you had phase boundaries in your data, and if so, what are the phases that you see?
Yeah, so far this is an observation in a single sample, and our only, if you wish, the things that we've explored are temperature, and there the phase boundary is the magnetic transition that we see. So it's there all the way from zero temperature up to this maximum temperature where magnetism disappears. It would be nice, we have got some samples where there's some doping to see how far this thing survives as you dope away from this parent compound. But we don't have any data on this. Apart from this, I'm trying to think of what other axis we could probe to look for a phase boundary. And I don't know. Maybe if you have some suggestions on what else would be an interesting axis to go along, that would be, I should think about it.
Yeah, well, any kind of magnetic phase, of course, would be interesting and relevant.
Yeah, so here, we've explored the application of an out-of-plane field, as I said, and it appears to survive till several Teslas. At least we could go up to 11 Tesla, and it survives up to that. More than that, I don't know at this point.
Okay. Well,
Thank you.
yeah, last question. Yeah.
Yeah, hi. Very nice work. So I wanted to follow up on Peng Sheng's question before regarding domain structure in this pair density wave state. So you showed a pattern which seems to be very field and temperature independent once you have it. So now you warm above TC, above TN, and it is gone. Now
Yes.
you cool back down. Will you get the same pattern in exactly the same fashion, or will it be different?
Yeah, so I believe this is true. Let me see if Her is on this call. He might very well be on this call. So I don't want to say something that he will then beat me on the head for, but I believe that one experiment he's done along these lines is to apply a field and take off the field and seen the pattern rotate. I believe that something like this has happened, but I could be wrong. I could be wrong on this.
No, but here I was wondering, just warming through TN, get rid of the pattern, and then cooling back down and watch it come back.
Yeah,
did you get it in the same way, or is it different, that maybe turned by 90 degrees or something?
Yeah, so this is a somewhat non-trivial measurement, but
Okay.
I believe that we have tried it, and I believe it comes back in the same place. If Her is here on the call, he can clarify whether this is true or whether I'm making this up.
Maybe she's not on the email.
Correct. You are correct. So we never seen rotation of the PDW stress.
Okay.
Well, it comes back in the same way as you had it before on the first go.
Right, almost exactly the same.
Yeah, okay.
Okay.
And if I may ask one other question, you said the crystal cleaves on the rubidium layer. So 50% of the rubidium stay on the sample and the other 50 go away with the top part, or how does this look?
Very good. You're absolutely right. And
He actually had a slide on that, I believe.
yeah. So these dashed ones, I believe, or whichever, one half of them do disappear. And something that we are lucky in this compound, there are other compounds of this type where they disappear in a very bad way. So, a whole region of it disappears, and then there's another region which doesn't disappear. On this compound, every second one disappears. And so it gives you half the rubidium, but in a nice ordered lattice on the top. Does that make sense?
This is truly remarkable, isn't it?
Well, nature is always a star.
Yeah. So you do have, in a sense, a very nicely reconstructed surface.
Okay, so I would call a reconstruction something where
Yeah, I know. I was, yeah, okay.
Let's not argue about terminology. Yes, to have sort of charge balance, but those that are there have a very nice ordered structure. This is really helpful because if they were to be disordered or do other bad things, we would be in trouble.
Okay, that's interesting. Thank you very much.
Thank you.
Okay, yeah, this is a really nice talk. I mean, I think really summarized the status of the field clear, but I guess the problem is still unresolved, right? We cannot declare victory on FFLO.
Yes, so this is certainly not I didn't mean to give that impression that this is an FFLO state or that this is a pair density wave state. All I would say is that we've seen a superconductor where there's modulations of the gap that are periodic in space. And this is due to the interaction between superconductivity and magnetism. And that's
clear. That's clear.
Yeah.
Yes, thank you very much, Abhay. Yeah.
Okay, you're very welcome. Thank you all for listening.
Yes, thank you, everyone, for attending.